Okay, so did you guys try to solve this topology? Try to find out the loop tree topology here.
नहीं मैंने नहीं किया.
Srinivas, did you try?
Actually, I was in office last 2 days. I have worked on
Uh,
migration, something like.
okay, no problem. So let's try to solve it.
Okay.
So give me, guys. We'll start in another 5 minutes. Okay, so did you guys try to solve this? Well, Prashant.
Hello Laksh, I did not solve it because I did not went through the recording.
Okay, that's okay. That's no problem.
Yeah.
So, okay, let's try to solve it right. So what I'll do, okay. So as we had assumed that the priority is 32,768, right? And the cost is going to be 1. And the MAC addresses is respectively their numbers 112233. So with these two conditions, where the priority is 32,768, right? So obviously all of them will have a tie of priority. So the next election for the root switch. Okay, so we are looking at the step 1. So priority is 32,768 and it's a tie between all these switches. Now the next tiebreaker would be which switch has a lower MAC. So as per our assumption, obviously this switch number 1 will have a lower MAC address. Right? So switch 1 becomes the root switch. Right? Then what we do, the second step is to find the root ports on all the non-root switches. Right? That's what our next step is. So what we are going to do is on all the non-root switches, starting from 2, 3, 4, 5 up till 8. What we'll do, we'll try to find out root ports on each switch. Now we know that root port is the port with which the non-root switch will reach the root switch or send data towards the root switch. That is the root port. Correct. So let's go to switch number 2 and check which interface is going to be root. As I said, there can be only one root. There may be multiple interfaces with which the switch can reach the root switch. However, there can be only one root. Correct. So over here, we can see this interface can be a root port. This interface can be a root. Now, then what the switch thinks, through which interface is the cost the lowest to reach the root switch. Right. So if you see here, and we have assumed the cost to be 1, correct? So the cost from 2 to 6 is 1. This is 2. This is 3. This is the lowest that I can see. This one also 1, 2, and 3. So both the interfaces, right? Both the interfaces of switch number 2 has a tie for the cost. Now we know that if a tie for a root port has happened because of a cost, the next step is the neighboring switch. Whichever neighbor switch has the lowest MAC address, that interface becomes the root port. So in our situation, 6 and 5 are the neighboring switches for 2, right? So 5's MAC address is lower than 6, and hence this interface becomes the root port. So I am keeping green as root port. Okay, green is root port. Okay, any question here? How this interface is root port? Cost is a type. When cost is a type, then the switch checks the neighboring switch's MAC address. Whichever switch has a lower MAC address, that interface becomes the root. All right. Then going to 3, obviously this is directly connected to the root switch, so this becomes the port 4. For 4 also, the directly connected interface could become the root switch. Obvious reason, because the cost is 1. no other interface will have a lower cost. Right. Similarly, the same explanation goes for 3. Right. This interface will have a lower cost to use the root switch. Hence, that becomes the root port. All right. Then coming to 4, 5. Okay. So 1, 2. Right. Then 1, 2. Then we have third 1, 2, 3, 4. So obviously, this interface cannot be a root port because that has a higher cost. However, we have 2 other interfaces where the cost is same, right? One via 3, the other via 8, right? This is 1 plus 1, 2. This is 1 plus 1, 2, right? So the interface or the spanning tree cost for both the interfaces same. The next tiebreaker is which neighboring switch has a lower MAC address. Obviously, 3 has a lower MAC address than 8. So this interface becomes the root port for switch number 5. Then on switch number 6, which is going to be the root port, again, 1 plus 1, 2, 1 plus 1, 2. Cost is a tie. Okay, when cost is a tie, the neighboring switch, whichever has a lower MAC address. 3 has a lower MAC address than 4. Obviously, this interface becomes the root. Then 7. 7 also has the same cost. When the cost is a tie, the lowering, the
MAC
switch with the
address.
lower MAC address. So this interface becomes the root port. Then 8. For 8, the directly connected interface becomes the root. Right. So we are done with the root port election on the non-root switches. Any doubt, any question with the root port election?
No, I'm good.
Okay. Nivas, Vivek, any doubt over here?
No question from my.
Now the next one is the designated port. Elect a designated port. Okay, so I'll choose this orange color as a designated port. This designated. So we know that all the interfaces of a switch except the root port is a designated port, right? All the interfaces of a switch except the root port are designated port. Okay, so on your non-root switches, all the interfaces except your root port is a designated port, and on the root switch, all ports are designated. So on the root switch, all your ports are designated ports. Then on all your non-root switches, every other interface except the root port is a designated. So for 2, 3, 4, 5, 6, 7, and 8. Okay, so these are the designated ports for all these switches. Then finally, the block port. Okay, it needs to find out which interface would be a block. We know that we can have a root port, designated port connectivity. We can also have a designated port to a block port connectivity. However, we cannot have a designated port to a designated port connectivity. In such a condition, one of the interfaces should become a block port, right? And we know that which interface would become whichever has a higher cost to reach the root switch. If that is a tie, whichever has a higher MAC, that switch would convert its designated port to a block. All right. So let's go for from 1, right? So let's check. Is there any DP connectivity? No. This is a DP root port. DP root port. DP root. Okay. So with this, we are very clear that any switch which makes a connectivity with the root switch, any non-root switch which makes a connectivity with the root switch cannot have a block port connected to root switch. Is there any block port between root switch and a non-root switch? No. Please remember, a block port cannot exist when it is connected to a root. Okay. So moving on to switch number 2. Do we have a DP-DP connectivity? Yes, between 2 and 6. Between 2 and 6, we have a DP-DP connectivity. So first criteria, which switch has a higher MAC to reach the root switch? Okay, 1 plus 1, 2, 1 plus 1 plus 1, 3. So 2's cost is higher to reach the root switch, and hence 2 will change its designated port into a block port. Okay, clear? Any problem with this? Okay. Now moving to 3, we have root port DP, DP and a root port and a DP, root port and a DP. So there is no problem with 3. Moving into 4, between 4 and 6, we have a DP-DP connectivity. Right. So which switch has a higher MAC to reach the root switch? Obviously 1 plus 2, whereas 4 is directly connected. So 6 will convert its interface to a block. All right. Now,
Yeah.
is there any other interface? 4? No. 4. Then moving to 5. Do we have DP-DP? Yeah, between 5 and 8. Right. So 5's cost is obviously higher, 1 plus 1, and 8's is directly 1. So 5 will convert its designated port to a block port. Then coming back to 6, we are done with 6 already because it's all the other connected interfaces are blocked. Then moving to 7, between 7 and 8, we have a DP-DP connectivity. Obviously, 7's cost to reach switch number 1 will be higher. Right.
Yeah.
So
7 will be blocked.
7 will block the interface. For 8, we don't have to anything. Now, if I remove, okay, before I jump to the conclusion, any problem? Anyone has any problem understanding this block port criteria?
It looks very easy now.
Yeah.
Yeah.
Okay, so now let's remove all the block port interfaces or the connectivity. This, and this. Okay, so this is your loop-free environment that is created by the spanning tree. This is your loop-free environment. The physical interfaces are there. However, because the interfaces are blocked, the blocked interfaces do not send or receive any data. That is why those interfaces, I have removed it from the topology, and this is how your loop-free topology looks like. Okay. So now if 7 wants to talk to 8, okay, if 7 wants to send a data to 8, it cannot send through the block port interface. It has to go like this. If 2 wants to send a data to 6, it needs to go like this. If 5 and 8 want to talk to each other, they need to talk like this. So this is how a spanning tree protocol creates a loop-free environment. Okay, clear? Any question? Anyone? Yes, this calculation is done automatically by the spanning tree protocol. We don't have to do anything. As I explained in our earlier class, spanning tree is enabled on Cisco switches by default. The moment you connect the switches together like this, they will automatically start to run spanning tree protocol and they will form a loop-free environment. So now we know the logic behind the switches of how they create a loop-free environment. Okay. Any question over here? Anyone? Now, another thing to be noticed is that all the calculation that has happened is used or is based on where your root switch is placed. The root switch is switch number 1. And that is why all your calculation has happened based on the root switch. If your root switch change, let's say some other switch takes over the role of a root switch. Let's say switch number 4 over here. Switch number 4 over here takes the role of a root switch. Then what would happen is your topology would be completely different. Because your cost, your root port election, your designated port election, everything happens where your root switch is placed. What is the cost to reach the root switch? To the root port. What is the cost to reach the root switch? To the block port. All that calculation happens because of where the root switch is placed. So based on your requirement, okay, based on your requirement, you can also change the root switch. Right, we will try. We'll talk about that later. But based on your requirement, where you want your root switch to be placed, how you want the traffic to flow, how many users are there in your network, between which two switches is the most traffic flowing. Based on all that calculation, you would be required to change the position of your root switch. Okay. Yeah, I'll come to this point. So Mohit has asked, what's the drawback of spanning tree? Why RSTP wasn't? Okay. So moving on with that topic or the spanning tree topic, we saw some roles, okay, or yeah, roles, port roles especially. Okay, so what are those port roles? Obviously, on a root switch, we have designated ports, right? Then on a non-root switch, we have a root port, and we also have a block port, correct? These are the port roles. Now, to achieve these port roles, a particular interface, it can be any interface, it can be a designated port interface, a root port interface, or a block port interface. To achieve these roles, though those interfaces go through port states, different port states. Okay, so the first state that any interface is at down is the down state, meaning that down or disabled, meaning the spanning tree is not yet enabled on that interface, or that interface is not connected to any other device. So it is down or it is disabled, right? The moment that particular or the moment an interface is connected to a switch or any other device, right, it moves to a state, called as listening state. Okay, listening state. We'll talk about listening state in detail in some time, but it is in the listening state for 15 seconds. Here is it is in the listening state for 15 seconds. Once this listening state is or the 15 seconds is over, it moves into learning state. That interface also remains in the learning state for the next 15 seconds. Once this 15 seconds is also crossed, it goes into any of these states based on the situation. It can be a root. If it is let's say that interface itself, not interface, switch, that switch itself is elected as a root switch, then all the interfaces of that root switch after these 30 seconds has passed will move into forwarding state, but in the forwarding state, they would go into a designated port role. Designated port role if it is a root switch. If it is a non-root switch, that interface may go to a root port role as well. right? And one of the interface of the non-root switch may go into a designated port, and one or more interfaces of the non-root switch may go into a block port. But when it is in the block port, it goes into a blocking state. So you have 4 states basically: down, listening, learning, then forwarding or blocking state. So if it is a root switch, let's say, let's go back over here. Let's say the spanning tree election is happening between all these switches, right? So the moment this switch is selected as a root switch, all the interfaces of this root switch will go through the listening state, learning state, and then they will go into a forwarding state. When they go into a forwarding state, all these interfaces go into the designated port row. Then let's talk from switch number 6 perspective. So when switch 6 goes through all the listening, learning state, one of the interface goes into a blocking state, the other interface goes into a designated port state, the other interface goes into a root port state. Not state, role. So there are, on a root switch, there is only one role, designated port role. But on a non-root switch, you will see a designated port role, a root port role, and a block port. Okay, so all these switches, they go through these 4 states before moving into either a forwarding state or a blocking state. Clear? Any question?
No, sir.
All right. Now, we have been talking about these roles and states, and we have been talking about elections, right? Designated port election, or root port election, or a root switch election, right? But how are these elections basically happening? If a root switch is elected, we know that a root switch is elected a root switch is elected based on the priority and based on the lower MAC address, right? So how are all these switches? How do they communicate about their priority? How do they communicate about their MAC addresses? Until and unless switch number 1, or until and unless all these switches in the topology, they know about each other's priority, they know about each other's MAC address, they cannot make this decision of whether it is a root switch or it is a non-root switch, whether it should be a root port, designated port, or a block port, right? So some kind of information or some kind of messages is being exchanged between these switches. That is why they are able to make this decision or the elections, right? That message is called as spanning tree protocol, BPDUs. It's called as bridge protocol data unit. Bridge protocol data unit. Now, let's first try to understand what is a protocol data unit. What is a PDU? Now, PDU is a kind of a language. It's kind of a language for a particular protocol. Right. Now, just like we have languages, right? So I take classes in English, right? I take it in Hindi as well, and then I take it in Tamil as well. So these 3 are the languages. These 3 are the languages that I can speak fluently and understand as well. Read, write, anything. So these are the languages, or in networking terms, these are the PDUs that I understand. And similarly, in networking also, for every protocol speaks its own language. So let's say OSPF, EIGRP, spanning tree. Let's imagine that. Okay. So OSPF has its own language with which it sends information to other OSPF speaking routers. Right. Similarly, EIGRP has its own language with which it speaks to other EIGRP speaking routers. Similarly, spanning tree protocol has its own language with which it communicates the information to other spanning tree speaking switches. And what is that? OSPF has its own hello message. We know that. OSPF has its own hello message. Hello message carries some kind of information. Similarly, EIGRP has its own hello message where it carries some information. Similarly, spanning tree has its own BPDUs, right? Spanning tree has its own BPDUs where it carries some kind of information. Okay, so think of this perspective. I speak English. You can also understand and speak English. That is why you have joined this class. Because I speak English and you can also understand English, we are able to communicate to each other. Right. Now, imagine if I speak Tamil and if I try to share some information with you where you can only understand English. Right. Similarly, you are speaking in English, but I can understand only Tamil. There can be no communication. There can be no communication. It can happen if you have a translator. Right. Where in networking, this translator is basically your redistribution. We're not going to talk about redistribution. Okay, but just understand redistribution. So if OSPF wants to speak to a router, it needs to find out a router which also understands OSPF messages. Similarly, EIGRP, if he wants to talk to another router which also, if he wants to send a message to another router, it should also understand EIGRP messages. Similarly, for spanning tree protocol, any switch which is running or sharing information about spanning tree, it should speak spanning tree messages so that the other switches can also understand the spanning tree information. Right. And what language do these spanning tree switches speak? They speak the message or they speak the language of bridge protocol data unit or BPD. Because it is spanning tree, it is called as a bridge. As I said, OSPF has its own PDU, which is called as a hello message. Hello message contains some kind of information. EIGRP also sends hello messages, but it has a separate kind of information. Similarly, spanning tree also has its own language, which is called as a BPDU, and with BPDU, it shares some information. All right. Any problem understanding what is a PDU?
No.
No.
Okay. So now, as I said, when they share information, obviously, when they are sharing BPDUs or when they are speaking their same language, they will be sharing the information, right? So in your BPDU, Bridge Protocol Data Unit, what are the information that a switch basically shares? Or let me contents inside a BPDU. So the first thing is the root switch priority. What is the priority of the root switch? Second information is root switches MAC address. Then the third information is its own MAC address, own priority. Fourth, its own MAC address. Right. Then the fifth is its cost to reach the root switch. These are the 5 most important things that is inside a BPDU and with which a spanning tree switch shares or talks with other spanning tree switches. So in this topology here, all these switches would have shared their own BPDUs with each other. That is why they were able to understand the information that is sent or received, and hence they were able to make this loop-free environment. Correct. Now let's understand this from a switches perspective. So this is a switch 1 and switch 2. Again, switch 1's MAC address is 111, switch 2's is 22. Now when switch 1 and switch 2, please understand, when a switch is powered on, or when the as I said, in Cisco switches, the spanning tree is enabled by default. The moment you connect these two switches together, they will start sending BPDUs to each other. And what are the contents inside a BPDU? These are the contents inside the BPDU. So let's imagine switch 1 and switch 2 have been connected just now. So what is going to happen? Switch 1 will send his own BPDUs. Switch 2 will also send his own BPDUs. And please remember, BPDUs are sent at every 10 seconds interval. 10 seconds, sorry, not 10 seconds. 2 seconds.
2 seconds. 2 seconds.
2 seconds interval. Okay. Please remember, BPDUs are sent at every 2 seconds interval. Okay. So switch 1 will keep on sending its own BPDUs in 2 seconds. The same goes for switch number 2. Now, when switch number 1 sends its own BPDU, what does it do? As I said, they have been connected just now. Right. So switch 1 will assume that it is the root switch. It will call itself as the root switch. So the first message, root switch priority, which is 32.768 by default. Second, root switch's MAC address. It will share its own MAC address. Third, its own priority, because it is the priority is 32.768. Its own priority is also going to be 32.768. Its own MAC address 1111. Right. Then what is its cost to reach the root switch? Since it is assuming itself as the root switch, the cost is going to be 0. Right. The same criteria or BPDU contents will be created by switch 2. Switch 2 will say, I am the root switch, so the priority is 32.768. Right. MAC address is going to be 2222. Third, its own MAC address 32.768. Fourth, its own priority, its own priority and MAC address 2222, and its cost to reach the root switch. Since it has assumed that itself is a root switch, so it is 0. Right. Now they exchange this BPDU with each other. So what is going to happen? They will go step by step. First, they will compare the priority. Priority is a type. When priority is a type, they move to the next step. Whichever switch has a lower MAC address, they compare their MAC addresses. So obviously, switch 1's MAC address is lower. Switch 2's MAC address is higher. So when switch 2 receives this BPD from switch number 1, it learns switch 1's MAC address. Right? It learns switch 1's MAC address, and it understands that switch 1's MAC address is lower than its own MAC address, and hence, if it is a lower, if the other switch has a lower MAC address, obviously this guy cannot be the root switch, so obviously he has to be a non-root switch. Right? If he is a non-root switch, this guy is a root switch. What is this port going to be? It is going to be a root port. Right? So this is how two switches, when they are connected together, this is how they make that decision. Which is going to be a root port, which is going to be a root switch, designated port, block port, etc. So in our topology over here, the moment we connected all these switches together, they have exchanged their own BPDUs. In that BPDU, they shared the root switch. The first time when they are enabling spanning tree, all of them would have assumed that they are the root switch. But the moment they see each other's MAC address, and BPDUs, as I said, BPDUs are exchanged at every 2 seconds. So what is happening? These BPDUs are being sent to all these switches. So indirectly, what is happening? All these switches would eventually know this guy is the root switch because he has the lowest MAC address of all. And based on that, they will start making those decisions of electing a root port, electing a designated port, electing a block port, etc. Clear? Any question about BPDU?
No.
Mohit?
Suppose
Yeah, Prashant.
suppose like any switches miss the BPDU, right? By XYZ reason. Then what happen?
Okay. So let's say for some reason, okay,
Yeah.
for okay, first of all, BPDUs are, as I said, BPDUs are sent at every 2 seconds. Who sends these BPDUs? BPDUs are sent only by the root switch, not sent. It is created only by the root switch. BPDUs, as I said again, please remember, BPDUs is created only by the root switch. So at every 2 seconds interval, he sends the BPDUs, right?
Okay.
These BPDUs are forwarded to each other through the non-root switches. Okay.
Mhm.
Now, let's say for some reason this interface went down.
Mm.
For some reason this interface went down. So what is happening? Switch number 5 would be expecting BPDUs on its root port. Okay. Another thing to be like remembered is that the BPDUs are received on the root port. BPDUs are always received on the root port, not on any other ports. Is received again, received, not sent. Received. BPDUs are received only on the root port. So here also in this diagram you can see BPDUs are being received by the switches on their root port. So if he sends a BPDU, it is received by 3 on the root port, received by 4 on the root port, 4 forwards it to switch number 7, which is 7 receives it on root port, root port, root port, root port, root port. Okay. Now, as I said, for some reason, this interface goes down. So after 2 seconds, switch number 5 is not going to receive a BPD. Correct? For some reason, 5 did not receive a BPD. So what 5 will do? 5 will wait for 3 missed BPDs or 3 BPDs basically. It will wait for, not missed, it will wait for 3 BPDs, meaning 6 seconds. It will wait for 6 seconds to receive a BPD. If it does not, what it is supposed to do? 5 will try to unblock this interface. Unblock this interface. Because anyway, this is blocked. He needs to unblock it so that from this side, BPDUs can be received. This is what actually happens. So when a switch stops receiving BPDUs, they will open their blocked interface so that from the blocked interface, the BPDUs can be received. And 5 now has an alternate path to reach the root switch.
Okay.
Clear?
So the
Yeah.
alternate port, right, which was blocked previously,
Uh,
that will become the root port now, right?
So you said it absolutely right. So now this is no more a root port because you are not receiving any reproduce from there, right? Which becomes a root port. This guy then becomes the root port. Because from here only you're receiving the root port, and from this interface only the switch number 5 can send data towards the root switch. Clear?
Yeah.
So
Yeah.
you are right.
And one more question which I have faced recently on spanning tree, like what is the convergence time?
Okay, yeah, we will discuss that.
Okay.
Okay, did everyone get Prashant's question and my explanation?
What he asked was, I didn't hear like something. It is, I didn't hear that.
Okay, no problem. Anyway, we'll be discussing. Okay, so this is the root switch. Okay, this is the root switch, and if that is the root switch, this is the root port. This is the root port.
Root port.
Right, for switch number 3, we have two root ports. Right, one is this way, the other is this way. Right, so cost is a type. When cost is a type, the neighboring switches MAC address, whichever switch has a lower MAC address, that interface becomes the root. For switch number 3, this interface becomes the root port. Right, all of them are designated ports. Right, when all of them are designated ports, designated DP, DP, DP. So now between switch 4 and 3, you have DP connectivity, right? So whichever switch has a higher higher cost to reach the root switch will convert its interface to a block. So this interface goes into a blocking. So please remember this diagram. I will be using this diagram frequently from now on. Okay, and the same topology. Now, what Prashant asked, I'm going to explain it over here with these four switches. So switch number 3 over here. Okay, switch number 3. Okay, let's first discuss few things. There is something called as a direct topology change. The other is called as an indirect topology change. Now, what are these? The first, direct topology change. Okay, direct topology change. Now, when we are speaking a direct topology change, we are speaking from the perspective of those switches which have a blocked interface. Okay, be it a direct topology change or be it an indirect topology change, we are speaking from the perspective of the switches which have a blocked interface. So switch number 3 in this scenario. Okay, just give me a minute. So direct topology change. Over here, let's imagine that for some reason, the interface between switch 2 and switch 3 goes down. For some reason, the interface between switch 2 and switch 3 goes down. And just now I explained, root switch is the only switch that creates the BPDs. So in a normal scenario, what is happening? Root switch creates BPDs. It sends it to all the switches that are connected. Switch 2 will receive it and will forward it to switch 3. Similarly, switch 1 will forward it to switch 4. Switch 4 will forward it to switch 3. However, to the blocked interface, it is not going to receive it. Okay, it is not going to accept it on the block. Right? Is everyone clear with this scenario or this explanation? the root switch will send BPDUs at every 2 seconds interval. Okay, it is sent to switch number 2. Switch number 2 will forward it to switch number 3. Switch number 1 will forward it to will send it to switch 4. Switch 4 will forward it to switch 3. However, because of a blocked interface, switch 3 is not going to accept that BPDU. Okay, is everyone clear over here?
Yeah.
Now, direct topology. Let's imagine that for some reason the interface between switch 2 and switch 3 goes down. Right. Now what is happening? Switch 1 forwards the data, forwards the BPDU to switch 2, but switch 2 is unable to forward. Switch 1 forwards the data to switch 4. Switch 4 is forwarding to switch 3. However, because of a block port, it cannot accept the BPDU. All right. Now, if you see in this scenario, switch 3 is completely isolated. If switch 1 is forwarding a data, or any switch is forwarding a data to switch 3 cannot receive it. It is completely isolated. Right? So in such a scenario, what switch 3 is supposed to do? Right? If switch 3 can reconnect to switch 4, now switch 3 will also start to receive a data. Correct? So to have such kind of a scenario, switch 3 is supposed to unblock its interface. Right? Now, how switch 3 is going to do? So as I said, at every 2 seconds, the BPDUs are sent. So switch 2 is sending BPDU, but it is not being received by switch number 3 because of a fault. So switch 3 waits for 3 missed BPDUs. So basically 6 seconds. It waits for 6 seconds. When it does not receive any BPDU on its root port for 6 seconds, what it does, it basically unblocks this interface. Okay, it unblocks this interface. When it unblocks this interface, it will first go to the listening state. It goes to the listening state. When it goes to a listening state, as I said, I will be explaining these states in detail. That is what I'm going to do now. When it goes into a listening state, which is 15 seconds, it is basically listening. What is it listening to? It is listening to the BPDUs. It is listening to the BPDUs that are being sent at every 2 seconds. So with the BPDU, what would happen? Switch 4's BPDU is being sent to switch 3, where switch 4 will say, who is the root switch? Root switch is switch 1. Switch 1's priority, switch 1's MAC address. Switch 4 will its own MAC address. Switch 4 will share its own priority, its own MAC address, etc. via the BPDU to switch number 3. Now, after this 15 seconds of listening, the switch number 3 starts to learn those received BPDUs. Starts to learn those received it starts to learn those received BPDUs. Now, because it is learning, in the learning state, what is it doing? It is making all that decision. It knows its priority and its MAC address is not equal to switch number 1. Since switch number 1 is the root switch, it will become the non-root switch. Right? If it is a non-root switch, it needs to elect a root port. It needs to elect a designated port. It needs to elect a block port. All that calculation is being done in the learning state for the next 15 seconds. For the next 15 seconds, it makes that calculation. Once that 15 seconds is over, it will now finally connect the interface with switch number 4 and move it to a forwarding state. And in this forwarding state, now because BPDUs are being received on this interface, it will convert this interface to a root port and this interface will become a block. All right, clear? What is happening in listening state? What is happening in learning state? In listening state, basically, a switch is listening to the BPDs, right? In the learning state, it is calculating. If it is calculating, it can be a root switch. It can be a non-root switch. If it is root switch, it already knows all the interfaces are supposed to be a designated. If it is a non-root switch, it needs to calculate few more things, which is going to be a root port, which is going to be a designated port, which is going to be a block port. What is the cost to reach the root switch? All this calculation is happening in the learning state. And when finally that is done, based on that calculation, root port and designated port will move into a forwarding state. Block port will go into a blocking state. Clear? Any question? Srinivas, Mohit, Vivek?
No, sir.
So
No,
this
sir.
was direct topology change. So if you see here, as so Prashant, you asked, right? What is the convergence time? So in a normal scenario, when your switches are coming up and they're making that decision, it basically takes 32 seconds for any interface to go to either designated port, root port, or a block. How is it 32 seconds? 2 seconds for the BPDU, 15 seconds in the listening state, 15 seconds in the learning state. So in total, you have 32 seconds. In a normal scenario, in direct topology change, this convergent times takes 36 seconds. So you have 6 seconds for the BPDUs, 15 seconds for listening, 15 seconds for learning. You have 36 seconds in such direct topology change, where a block port takes 36 seconds to open its interface. 36 seconds. Clear? Any question?
Yeah. One question, Lakshya, like suppose any Ethernet port, right, between switch to switch communication, right? When we connect a new port, right? How long it take to come up, right? The port gets into first, like port is in disabled state, right?
Yeah, that is what I showed you here. 32 seconds.
32 seconds, right? Okay.
As I said, this is the normal scenario where you
Okay.
just connected the switch to an Ethernet port to a wire.
Okay.
Okay, the moment you connect a wire to a switch port, it takes 32 seconds to go into a forwarding state
Okay.
or any state, be it any state. It can be block port, designated port, root port, any port. It takes 32
Okay.
seconds.
Okay. Got it. I said, I think in interview during that time, I'm not sure what happened at that time. I said 45 seconds.
Happens. I remember blabbering. I'll talk about this at the like end of the session,
Okay.
where I was very stupid and overconfident.
Mm.
This was direct topology. Now, what
Okay.
could happen in indirect topology change? Okay, so direct topology change meaning there is a problem with the interface, like on switch number 3, right, where you have a block port. So as I said, these topology change that we're talking is from the perspective of those switches which have a block interface, right? Now, direct meaning there was a problem on switch 3 itself, which has a block. Now we are going to
Hmm.
consider a situation where there is a problem somewhere in the network and it is not on switch number 3. Okay.
Hmm.
Now what is going to happen? Check that. Switch number 1, switch 2, switch 3, switch 4. Root switch, TP, TP, root port,
RP,
root
RP,
port, root
root
port,
port.
and signal. Okay.
Okay. Yeah.
Now, indirect topology change. Let's imagine that the interface between switch 1 and switch 4 goes down. The interface between switch 1 and switch 4 goes down. Okay. So here in this scenario, what is happening? Root switch is sending BPDUs at every 2 seconds interval. Switch 2 is also sending BPDUs at every 2 seconds interval. In a normal scenario, switch 2 is sending BPDU to switch 4 and switch 4 is sending BPDU to switch number 3. However, because of a block state, it is not accepting that BPDU. Right. Now, when there is a problem between switch 1 and switch 4, what is going to happen? Switch 1 is sending a BPDU, however, switch 4 cannot receive it. If switch 4 cannot receive it, it cannot forward that BPDU to switch 3. Okay. Now, what is happening? Switch 3 is supposed to receive the BPDU on the blocked interface. However, now it is not receiving. That means switch 3 understood something is wrong. I'm not receiving BPDUs on the blocked interface. I'm supposed to receive it, but I'm not. Okay, so now what happens? Switch 3 will again wait for 6 seconds. That is your 3 missed BPDUs. Now, when 6 seconds are crossed, it again waits for 20 seconds. This wait period of 20 seconds is called as max edge time. So first, switch 3 waits for 6 seconds. That is your 2 seconds BPDU into 3 times. Right. Then it after 6 seconds has crossed, it waits for another 20 seconds. This 20 seconds is called as max edge time. Okay. Now, why is this 20 seconds needed? This 20 seconds is needed because switch 3 is hoping to listen or receive any BPDUs from switch number. Because there may be an interface flag. This interface went down. For 6 seconds, there was no BPDU. And after 6 seconds, let's say at 10 seconds. At 10 seconds, this link came up. Switch 1 sent the BPDU. Switch 4 forward that BPDU to switch number 3. Right. So it is waiting for that confirmation. Is there an interface flag? It waits for 20 seconds. Right. Now, even after 20 seconds, if the BPDUs are not received, then what happens? It will move into the listening state. It will move into the listening state. However, in this listening state, it is already listening from its root port. It is already receiving BPDUs from the root port. So it's okay in the listening state. Then after this 15 seconds has crossed, it goes into the learning state. Right, goes into learning state. Then after this learning state is over, it opens up its interface and connects it with switch number 4. Now, even if switch 3 has opened its interface, right, switch 4 on this interface will again go through that. 15 seconds listening, 15 seconds learning, then only it will go to the, 2 seconds of BPDU, 15 seconds listening, 15 seconds learning, then that is after 32 seconds only, this interface will start to receive BPDU or get the data from all the other switches. Clear? So basically what is happening in an indirect topology change, the total time taken by switch number 3 to open up its interface is basically 15 plus 15, 30, 50, 56 seconds. It takes 56 seconds for a switch in an indirect topology change to open up its block. Clear?
Yeah.
So if someone asks, like Prashant said, what is convergence time? What is the convergence? So in a normal scenario, the convergence time or any interface that takes any interface that takes time come up to any port role. It can be a designated port role, it can be a root port role, or it can be a block port role. It takes, in a normal scenario, it takes 32 seconds. Like if you connect two switches together, the interfaces like switch 1 and switch 2. If you connect these two switches together, these interfaces will take 32 seconds to come up. Okay. Now, in a direct topology change, the block port of a switch takes 36 seconds to come up. And in an indirect topology change, that same block port takes 56 seconds to come. These are the three different convergence: 32 seconds in a normal scenario, in a direct topology change, 36 seconds, in an indirect topology change, 56 seconds. Any question? Mohit?
No, sir.
Now, if you think from a real-time perspective, like in today, 2nd June 2025, if you think, can we wait for 56 seconds, or can we even wait for 30 or 32 seconds? No, right? The moment we connect our mobile phone to the Wi-Fi router, we want it to be connected immediately, but we can't wait for 56 seconds, or like 56 seconds is nearly 1 minute. We can't wait for 1 minute or half a minute. The moment we do not have connectivity, we start panicking that why is the internet not connecting, this, that, etc. We get frustrated. Right? We have all these problems. So this is actually a real problem. For 56 seconds, who's going to wait? For 36 seconds or 32 seconds, who's going to wait? Now let's take the same scenario. Switch 1, switch 2, switch 3, and switch 4. Now let's say I connect a PC to switch number 2. The moment I connect a PC to switch number 2, this interface is going to take 32 seconds to come up. Okay, I don't have that patience. I literally do not have that patience to wait for 32 seconds. Or let's say for some reason, there was a problem at my end. Imagine there was a problem at my end. Okay, so what is going to happen? Basically, if I have a problem at my end and I get I solve that problem and connect it back to the switch. The switch will again take 32 seconds to start forwarding data, right? To receive data or to forward data, it will take 32 seconds. I don't have that patience. So in order to basically do or lessen the time, we came up with something called as a port fast interface. Basically, interface is fast, or that port is fast. So we always enable port fast on those interfaces where we know they are being connected to an end device, where we are connecting them to an end device. It can be a PC, it can be a laptop, IP phone, IP TV, a printer, a Wi-Fi router, not a Wi-Fi router, a server, anything. When we are connecting a switch to an end device, we make sure that we enable port fast on that interface. Because the moment I connect that end device to this interface, I want it to start immediately forwarding the data. So interview question, what is port fast? What is a port fast interface? Okay, so port fast interface is an interface which is enabled on the switch, or not on the switch, on a switch where that interface is connected to an end device. Right? It doesn't. The speciality or the feature of a port fast is it does not wait for that 32 seconds. No, it does not wait for that 32 seconds. Immediately, 0 seconds. Within the moment you connect the end device on a port fast interface of a switch, immediately it will move into forwarding state. Forwarding, not blocking, not not in a blocking state. Forwarding state. And that also it is going to be a designated port, not a root port. Designated. All right. Port fast interfaces are those interfaces which are connected to an end device, and the feature or the specialty of a port fast interface is that it will immediately start to forward data, or it will immediately go into a forwarding state, and the port role is going to be designated port. Okay. Port fast. Any question or any problem with port fast?
No.
Now we are human. We make mistakes. Now imagine that I have a port fast enabled interface over here, and by mistake I connected a switch over here, switch 5, and let's say this switch 5's MAC address, or let's say priority. This switch's priority is 32768. Let's say this switch's priority is 4096. Okay, we know that the switches first compare the priority, then only they compare the MAC address. Here the switch 5's MAC address, priority itself is 4096. And I, by mistake, connected this switch number 5 to a port fast interface in an existing network. This is an existing network, smoothly running network. By mistake, I connected over here. What is going to happen? Switch 5 will immediately, or this interface will immediately go into forwarding state. This guy will start accepting BPDUs. The moment it starts accepting BPDUs, it will know switch 1 cannot be a root switch because switch 5's priority is lower. What will happen? Switch 5 will immediately take over the role of root switch. Then what is going to happen? The topology will completely change. Topology will completely change. Okay, so instead of a block port over here, I think this is going to have a block. Topology has completely changed. This is a simple scenario. You just have 5 switches. In real time, you have 50, 100, 150, 200. One single mistake can change your whole topology. Right. So in order for these mistakes to not happen, what we did, we created some protection methods. And those protection methods are called as guards. And what are they guarding? They are guarding the BPDUs. They are guarding the interfaces from BPDUs. Okay, so you have two types of guards. Again, an interview question. What is the difference between a BPDU guard and a root guard? Interview question. Okay, so let's go back to our scenario over here. Now, let's go to the root guard first. Okay, so over here, what is happening? Let's imagine I have like such a scenario. Switch 5 is connected. Now, let's say I enable root guard on this interface. I enable root guard on switch number 2 on this interface. So now, when switch number 5 sends BPDU, it is going to send its own BPDU with priority of 4096, correct? Switch 2 is already receiving BPDUs from switch number 1, where the priority is 32768. Right. Now, what is going to happen? Switch number 2 is going to compare these two BPDUs, switch 1's BPDU versus switch 5's BPDU. So it knows switch 5's BPDU is better, meaning switch 5 can become the root. Switch 5 can become the root, and that is why it has been enabled with root guard. Meaning, if on the root guard enabled interface, if it receives a BPDU, please listen to this carefully. On a root guard interface, if a BPDU is received which has a lower priority or a lower MAC address, lower priority or a lower MAC address. What is the meaning of lower priority? If it is a lower priority, obviously that switch can become the root. So I'm protecting my root. I am protecting my root switch, or I'm guarding my root switch from lower priority or lower MAC address. So when a lower priority or a lower MAC address BPDU is received, this root guard enabled interface will go into an error disabled state. Meaning, it basically blocks the interface. Blocks the interface. Now, what is going to happen? Even if switch 5 is connected, it's not going to accept any BPDU. So what is happening? Switch 1 is safe. This is the working of root guard. Clear? Any question? With the root guard, Srinivas, Mohit, Vivek.
No, understood.
Now, again, there is a problem. As I said, root guard only works when you have a lower priority or you have a lower MAC address. Let's say I connected switch 5 to the switch number 2. It has a normal priority, that is the default priority, 32768, and the MAC address is 5555. Now, what is going to happen? Root guard is enabled and it works only if you have a lower priority. This guy does not have it, it has an equal priority, then it moves to a MAC address. This guy has a higher MAC address. What is the problem? So switch 5 then gets connected to your network. Switch 5 gets connected to your network. This is a problem. Let's say I have a PC connected over here. Okay, this guy is a threat. He's an intruder. He can increase this. He can increase switch 5's priority and get connected to switch number 2, thereby gaining access to the network. So it's a problem. So in such a scenario, what are you supposed to do? So in such a scenario, it is better to enable BPDU guard. Now, root guard checks only lower priority and lower MAC address. BPDU guard, whereas BPDU guard does not care if the priority is low, if the priority is high, if MAC address is low, if MAC address is high. It does not care about it. If I receive a BPDU, that BPDU can be better BPDU or can be a worse BPDU. I don't care. If I receive a BPDU on the BPDU guard enabled interface, I will block this interface. I don't care if it's a higher BPDU, lower BPDU, I don't care. It is a BPDU. I received a BPDU, I'm going to block this interface. So instead of enabling root guard on your switches, it is always better to enable BPDU. No matter what kind of BPDU you receive, it will go to a blocking state. Since you are the admin, you can go check which switch is connected to this interface. Is it a correct switch? Is it a reliable switch? Do I really want this switch to be connected over here, etc.? Make all that decision, then either disable BPDU guard or let it be there. It is up to you. This is the difference between root guard and BPDU guard, and this is an important interview question. Root guard always blocks lower priority and lower MAC addresses. Lower priority and lower MAC address. It always blocks this. However, BPDU guard blocks all
Everything.
BPDUs.
All BPDU.
It blocks all BPDUs. Now, it is not necessary that the BPDU guard and root guard is supposed to be enabled only on port fast interfaces. You can enable on any interface. You can also enable BPDU guard over here. Here, root guard, anything you can enable. It's not necessary that you have to enable on your port fast. Port fast is enabled only on those interfaces where you are connecting an end device. And as a security measure or a protection, you enable BPDU guard on port fast interface also. Let's say switch 3 has many empty interfaces, right? It has many empty interfaces. I can just simply connect a laptop over here and start sending data, right? I do not want that. So what I will do, on all the empty interfaces of a switch, I will enable BPDU guard. I will enable BPDU guard. Okay, now yeah, I will enable BPDU guards. Clear?
Basically, we are enabling the BPDU guard, right, on switch number S3 because there we are expecting like subscriber will be connected and subscriber will not send BPDU, right?
Correct. If subscriber cannot send BPDU, obviously it can be connected. It can be directly connected.
Yeah.
There's
Yeah.
no problem there.
Yeah.
It can be directly connected. This is also a loophole. BPDU guard checks only BPDUs. It does not check real data. Right. So here only you have security that comes into picture. So when you connect a PC to a switch and when it starts to send data, right, it asks, what is your credential? Tell me your username, tell me your password. Then only I will allow you to send data. So this is where your AAA, TACACS and radius server authentication comes into picture.
Yeah.
Clear? Any question?
Sir, I
So,
have one question here. Yeah,
Yeah.
Prashant, sir.
Yeah, no. Carry on. Yeah, you can ask Vivek.
So,
I will ask
uh,
later. Yeah.
here you mentioned root guard. Root guard only block the lower priority and lower MAC address, right?
Correct.
So if root guard receive the higher priority and higher MAC, so it won't going to block that BPDO, right?
Yes, it is
Okay.
not going to
So
be.
okay. So suppose if anyone asks in interview, so we can say these two lines also, right? BPDO guard will block all BPDO, no matter lower or higher, and root guard will only block the lower priority and lower MAC address, right?
Yes.
Okay.
That is why BPDU guard is preferred over root. Now, Mohit, coming to your question, why RSTP is used? I'll explain that to you. The working of RSTP is exactly the same as the normal spanning tree protocol, but why is it rapid? We'll talk about that tomorrow.
Like sir, just one question, right? When we in even in our production, right? However, I'm not working currently on STP. So when suppose you are working in Cisco, you deployed new switch in your lab. So what kind of do you configure rapid spanning tree? Because by default, spanning tree is configured in switches, right?
Hmm.
So which
So
type of spanning tree, like which flavors of spanning tree do you configure in your environment?
we usually go ahead, see, in Cisco switches, it's uh, by default, your rapid spanning tree is enabled.
Okay.
It is rapid spanning tree that is enabled. Spanning tree is no more, actually, it's not existing anymore. Because
Mm,
as I said, no one has time to wait for 32 seconds, 36 seconds, 50 seconds. They have no time to wait. That is why we brought up rapid spanning tree protocol. Okay. So on Cisco switches, by default, as I said, when spanning tree is enabled, it is actually rapid spanning tree that is enabled. Now, with rapid spanning tree, we also enable per VLAN spanning tree also.
mm,
Okay, so we change the mode of rapid spanning tree to per VLAN spanning tree. Now they have integrated per VLAN spanning tree and rapid spanning tree together. So
okay.
the timers, the convergence time of rapid spanning tree is now integrated with per VLAN spanning tree. So even if you change the mode of spanning tree to per VLAN spanning tree, it works. The convergence time is still less, just like your rapid spanning.
Okay.
Any other question? Anyone?
Sir, just like in this topology, right? S1, S2, S5, S4, S3, right? So basically on S2 we have configured BPDU guard enable, right? So it means, right, whatever BPDU I am receiving from switch 5, right, I'm just going to discard that BPDU.
Yeah.
So and I have just deployed a new switch 5 in my network, being a network
Okay.
admin, and 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 I'm believing that there are some intruders like outside who is connected on my switch 5 who is sending malicious traffic in my network. Okay, that's why I have enabled the BPDU guard on my S2 switch so that I can save my network, right? And on switch number 5, right, I have but a few other customer who are like a valid customer. They want to access any PC subscriber server which is connected to switch number 4 or switch number S1.
Okay.
Then how we can achieve this?
First of all, you have to remove those malicious guys. Without that, you can't do anything. It's a collateral damage.
Oh,
You,
okay.
your those other subscribers who are not able to access, they will be hit. They will complain that
Okay.
we are not receiving any data. We have internet problems. Is that they will complain? You have to bear with that. But we have to first, sort this intruder problem. Then only you can disable BPD.
Okay.
Because
Mm-hmm.
that fighting that intrusion is more important than letting your customers have the internet, because you don't know what is the purpose of that intruder. Does he want to attack your network, or does he want to access other subscribers through your network? Okay, you don't know
Right.
their purpose. So first it's to fight the intrusion, then do whatever you want to do in your network.
Okay.